the environment like which is okay for
It's a
chemical reactions, like perfect.
no chemical reactions are occurring here. When we speak about chemical environment or chemical surrounding, it's usually just the, for example, if I'm focusing on just the carbon that is colored red, all right, just the carbon that is colored red, it has four different groups joined to it, right? Three of them are hydrogen and one of them is carbon. Yes.
Yeah.
Now, if you look at this other carbon, the second carbon atom, can you talk? Can you tell me about what groups that carbon is joined to? I mean, we can say it's joined to two hydrogen atoms, one chlorine and another carbon, right? What do you think? The second carbon atom, the carbon atom on the right hand side, that is joined with a chlorine, two hydrogen atom, and the carbon, obviously. I'll be a bit lost. Like you can see here, it is joined to a carbon on this side. That won't help.
Yeah.
It is joined to a carbon on this side, a hydrogen on the upper side, another hydrogen on the lower side, and a carbon on this side, right?
Yeah.
But if you consider the other carbon atom, that is the carbon atom that is on the left side, that is joined with a hydrogen, another hydrogen, another hydrogen, and the carbon on this side, right? Now, the two carbon atoms that we can see here, do they have the same chemical environment? So when I say chemical environment, just look at those carbon atoms and compare their surrounding, whatever's around them. Is it same? Is it identical for both the carbon atoms or not identical? What can you see here?
Like I didn't understand the question you asked.
Okay. Let me draw this again. One.
All right.
How many carbon atoms do you see here?
There's two carbon atoms.
Two carbon atoms. Now, are both the carbon atoms, do both the carbon atoms have similar atoms around them or different atoms around them?
Both of them have different.
Different, like their surrounding is different, right? Whatever is
Yeah.
beside them is different.
Yeah.
Are we clear on that, or are we not clear on that? We are clear on
Yeah.
that.
Yeah.
And because of that, we're going to say that there is the two carbon atoms have different chemical environment. That's what we mean by
Yeah.
chemical environment. Just the surrounding, whatever is around them. Okay.
Yeah.
Now, since there are two chemical environments, two different chemical environments in the carbon 13 NMR, you're going to get two peaks. Two peaks. Okay. So when I'm
All
talking
right.
about peaks, so what am I saying here? We looked at graphs like these yesterday, if you remember, and
Yeah.
we looked at propan 1-ol and propan 2-ol, and we saw that one of the graphs are having three peaks, the other one is having only two peaks. It depends on the difference. All right.
Yeah.
Now, this chloroethane, this compound here, it has two carbon atoms which have different chemical environments. So we can expect two separate peaks. Is that clear?
Yes.
Two separate peaks. Um, if you look at this compound here, this compound, it has three different carbon atoms. Yes.
Yes.
Now, if you compare the carbon which is this first one and the third one, these two actually have same surrounding. Do you agree, or like, can you see that or not?
Yeah, yeah.
Yeah. And what about the middle one? The carbon that is in the middle, it has a slightly different surrounding, right?
Yes.
So we can expect, so although there are three different carbon atoms, in actually how many different environments are there? How many different types of surroundings are there? Two, right?
Yeah.
There's actually two different surroundings. So in reality, you can expect two separate peaks from this compound as well. Is that is that fine?
Yes.
Two separate peaks. Now, I'm going to show you some examples with the peaks as well. Just try to understand the carbon environment, the chemical environment part. And what about this compound here? There's four different carbon atoms, obviously. Now
Yes.
here, obviously, this first carbon atom is a bit unique because it is joined to a chlorine, right? So it's natural that it has a very unique surrounding. Now,
Yeah.
what's most interesting in this compound is focus on this carbon atom, the one that is in the second and the third carbon atom. All right, focus
All
on the
right.
second and the third carbon atom. Now, the two carbon atoms in the middle, they seem to have similar environment, right? Their surrounding seems to be same. It looks as if it's
Yeah.
same, but in reality, we are going to say that it's different. All right, why is it different? It's different because this chlorine atom, it's affecting them. How is it affecting them? You can see that the carbon atom that is here, that is a bit closer to the chlorine atom, whereas the carbon atom which is here, that's a bit farther from the chlorine atom. Do we agree on
Mm.
that or not? Now,
Yes.
although their bonds, like what bonds these two carbon atoms are forming, it's identical, their chemical surrounding is still not, we will not consider them to be same. There will be some differences, all right? And obviously,
Yeah.
this fourth carbon atom, it is obviously going to be slightly different again because it is joined with three different hydrogen atoms, right?
Yes.
So in this compound, you have four different carbon atoms, and we can say that each of the carbon atoms have a unique surrounding. Their surrounding is different, right?
Yeah.
So since we have four different environments, we can expect four different peaks, all right, in the graph.
All right.
Four different peaks. Now, let me show you some examples of peaks. Just a moment. Um, Now, you can see this graph here, all right? Now, there, this is the graph, the carbon-13 NMR spectrum for this compound here, 3-hydroxy 3-methyl butane 2-on. Now, let me draw the structure first, and then we can explain the different carbon environment. So it's butane 2-on. So there's a ketone group in carbon number 2, and in carbon number 3, there is one hydroxy group and one methyl group. Okay, do we understand this
All right.
compound?
Yeah.
Okay, so this is one of the compounds. Now let's focus on the carbon atoms. All right, so you have
All right.
um, this is one of the carbon atoms.
Yeah.
This is another carbon atom. This is another carbon atom. Another carbon atom, and finally this is one more. So we can see here there's like 4 or 5 different carbon atoms, right? Now
Yeah.
let's look at their chemical environment, their chemical surrounding. Okay, let's look at
All
the
right.
chemical surrounding. Now, if you think about the carbon, atoms that are labeled red and brown. All right, the
All
ones
right.
that are circled red and brown. Do you think that they have same surrounding or different surrounding? What do you think?
Um, I think they have the same surrounding.
They have the same surrounding because they're
Yes.
both joined to the same carbon atom, right?
Yes, and they
And
have H3 as
individually,
well.
yeah, both of them are having like directly joined with three different hydrogen atoms. So
Yeah.
we can say that this carbon atom and this carbon atom, they have the same chemical environment. Now, if you consider the other ones, the green color, blue color, and the orange colored ones, the three of them are completely unique, right? They have completely unique
Yeah.
chemical environment. So overall, can we say that there are four different chemical environments? Can I say this or not?
Yes.
There's four different chemical environments. And so in the carbon 13 NMR, the spectrum, the graph, we can expect how many different peaks? Four different peaks. And you can see in
Yes.
this graph, there is exactly four, like approximately four different peaks, right? One,
Yes.
two, three, four. Can we see that or not?
Yeah.
All right. So in your exam, you will be experienced, like you will face these sort of graphs and you have to identify the values. So let me give you the values and then we can discuss 1 minute. The carbon 13 value. Let me we'll discuss. Yes. Um, so this will be given to you in the data booklet, so you don't have to memorize any of these values. All right. Now this will be helpful to you because you can use this to identify. Now let's try to make sense of the graph that we have got. Now consider the two carbon atoms. All right, the CH3, CH3, those the red color and the brown colored ones. All right.
All right.
So those two carbon atoms, they're mainly joined to the carbon atom, right? They're similar, they have the similar chemical environment because they're both joined to the carbon atom, right? The green colored
Yes.
one. Now in the diagram, in this table here, can you find out the value, the chemical shift value for carbon joined to a carbon? It's this one, right? Carbon joined
Yeah.
to a carbon, single bond. We will not consider this because this is arene. Arene is an aromatic compound. So for now, don't worry about that. Okay, that is also carbon-carbon single
Yeah.
bond, but we won't consider that now. So for this one, the value is approximately somewhere between 40 and 20. Okay, we can
Yeah.
expect that. Okay, so for this one, the value, the peak can be expected somewhere between 40 and 20. Consider the green color carbon atom. What's the main feature of the green color carbon atom? It's joined with an OH, right? That's why it's
Yeah.
very unique, the surrounding. And from this table, you can see that you have the COH group here. Can you see here? COH.
Yes.
And the value for that is approximately between 60 and 70, right? It's not 80, it's like
Yeah.
around 60 to 70. So green color one, the peak we can expect from 60 to 70. Uh, the blue color carbon atom, that is the main feature, is joined with carbon with an oxygen, right?
Yeah.
Carbon that is joined with an oxygen, and it's actually matching with this if you check, because it has two carbons on two sides, one carbon on that side and is joined with another carbon on that side as well. You can see
Yeah.
here. Let me zoom in, it's probably a bit too small. Can you see now clearly?
Yeah. Yeah.
So this carbon, it's also joined with one carbon on the left side, another carbon on the right side, similar to the one that we have used. Does it make sense? And an
Yes.
oxygen, double oxygen. And the value is expected from somewhere around 200 to 220. Is that fine?
Yeah.
All right, so we can expect the value from 200 to 220. And what about the orange one, the orange colored, um, the orange colored carbon? That is also a carbon, and it's also similar to the like it's joined with a carbon, another carbon, right? This orange
Yes.
colored carbon atom. So that is also this one only, right? So for that one also we can expect a value that is between 20 and 40 as well. The peak can be expected between 20 and 40. So although
Yes,
their
sir.
chemical environments are not exactly same, there are some differences, but the values will be very close. All right.
All right.
So let's try to now match it with the graph. So you can see here that from between 40 and 20, we have how many different peaks? We have how many different peaks between 40 and 20?
40 and 20, we have one,
Two different,
two
two
different
different
peaks.
peaks.
Yeah.
Why two different peaks? Because, which is very important, this carbon and this carbon, they have the same environment, right?
Yeah.
They are responsible for one peak. Does that make sense? They're
Yes.
responsible for one peak. And this orange color, this carbon is responsible for the other peak, that is around 20 and 40. Is it clear or not?
Yes.
All right. Look at the green color one. That one is responsible for a peak that is close to 70, 60, 70, somewhere around that, right? And that one is probably this
Yeah.
one only. This one, this is the only one that is closest to that region. Yes.
Yes.
And finally, the blue color one. Look at the blue color one. The value is from 200 to 220 that we saw from the table. And you can see here, there is another peak that is very close to 200 to 220. Does it make sense?
Yeah.
Like, are we understanding how to relate the values from to the graph?
Yes.
Okay, so this will be very important. We'll look at some mathematical examples later, but yeah,
All
uh,
right.
just a moment. Uh, okay, so as I was saying, uh, this question is about this graph here that is given to us. This is an NMR spectrum. So this graph is obtained after you did NMR spectroscopy. And we can use this to identify which structure is possible. All right, so the question told us that we have a molecular formula C3H6O, but we don't know what the structure actually looks like. Okay, now there's two possibilities here. One of them is this one or this. Okay, only
All
one
right.
of them is actually will be correct according to the graph, and we have to figure out which is correct. So let's use the table and try to figure out. All right, so let's look at the peaks first. uh, First peak around 200 to 210, right? Like, it's if I'm being very specific, can I say that this is around 203, 204, something like that? Because
Yeah.
this is 200, so this is probably 210, right? This is probably 210.
Yes.
So this must be less than 205, definitely less than 205. So let's just say, let's just make an approximation. It's around 204. Okay,
All
204.
right.
This one is around what, 38, perhaps 37, 38. You don't have to be
Yeah.
exact. You can just be a good approximation is fine enough. And the
All
third
right.
peak, it's can you tell me? Can you guess? Can you What approximate value can we take for the third peak? Third peak around 10. This is obviously 10, right? That's obviously 10. So
Yeah.
this peak is less than 10. So maybe like 8. Let's say 7 or 8. Let's say 7. Is that fine?
Yeah. Yeah. We can.
Okay, so these values that we get from the graph, these are all known as chemical shift. Okay, we talked about chemical shift yesterday, the basic of chemical shift, what chemical shift is. And chemical shift has a unit of ppm, okay, parts per million. Is that fine?
All right.
So now let's use the table, use this information, and try to decide which groups can be possible. So 204. So now you can see from this table here, 204. Above 200, we only have two possibilities, either this one or this one, right? Only two possibilities.
Yes.
So it can be a ketone or an aldehyde, right?
Yes.
Now, obviously, ketone is not a possibility because the structures that we are deciding from, these are the two structures that we are deciding from, right?
Yeah.
These two structures. Do either of them have a ketone or not? Can you tell me? Does either of them have a ketone functional group?
Uh.
They don't, right?
Yeah. No. No. They don't. They don't.
They don't. So first thing, so what can we decide initially? We can decide initially that the chemical shift at 203, this is due to the carbon oxygen bond, and this can be either in aldehyde or ketone. Okay, for now we know that it is possible with either aldehyde or ketone. This is our first observation.
All
The
right.
next graph, the next peak is at 38, right? 38.
Yes.
So let's use this table. 38. What possibilities are there? 38. I can see that this is a possibility at 38. It's very close to 38. This is a
Yes.
possibility at 38, and this is a possibility as 38, right? Because 38 is around
Yeah.
here, somewhere around here, if I'm not wrong. Do we agree or not?
Yes.
Okay. Now, can you tell me that it's very reasonable to completely exclude these two? Why is it reasonable? Why can we ignore them? Because those bonds, if you specifically take a look at those bonds, one of them is carbon nitrogen, carbon chlorine, carbon bromine, right?
Yeah.
So none of them are really present in what structures we have. What do you think? The
Yes.
structure that we have, they don't really have halogens or nitrogen. So it's possible, like it's okay to ignore them. So that
Yeah.
means we can conclude that it must possibly be it's only this one is one possibility. That's only one good possibility, right? The other ones are not
Yes.
don't really make sense. So we can conclude that the value of 37 or 38, which we have decided, the chemical shift at 38, it is responsible for the carbon carbon bond. Is that fine?
Yes.
Carbon carbon bond. Okay. And lastly, we have at 7, right? We have another tick at 7. Now,
Yeah.
7 is like here, like almost here. 7.
Yeah.
So the peak at 7, that's also only possible for carbon carbon bond only, right? No other bonds are really
Yeah.
available at 7. So same again, the chemical shift at 7, it's also due to the same carbon carbon single bond. Now, if you are thinking, you might have a question. If you're thinking that how is it that these are the same bonds, these are the same bonds, and why do they have this different chemical shift values, right? Because we know that
Yeah.
these two are possibly the same chemical environment. Then
Yeah.
why are they not having the same value? The reason
Yeah.
for
Yeah.
that is the reason for that is although the bonds are the same bond, apart from the bond, there are other differences. All right. For example, what atom is other than the carbon atom? So there are other differences which can cause differences in the chemical shift. All right. So even though the bonds are same, even though this is a carbon carbon single bond, this is also a carbon carbon single bond,
Yes.
the chemical shift values for both of them are still different because the chemical environment is still different. Is that fine or not?
Yes.
All right, so now let's try to decide. Let's try to use our structures and try to figure out which one is possible. So we can see there's three different chemical environments, right? One of them is for responsible for this one of them is responsible for that, one of them is responsible for that. Now, I think you noticed by now that we did not get any chemical shift for COH bond. Did you notice that?
Yes.
There is no COH bond. So possibly that means that this is not possible in our structure. And moreover, only this one is having aldehyde group, right? The other one doesn't even
Yeah.
have aldehyde group.
Yeah.
Even more importantly, this one has a carbon-carbon double bond. Do you see that? But
Yes.
did we get any chemical shift value that corresponds to a carbon-carbon double bond, or did we get nothing like that?
We got nothing.
We got nothing, right? So that possibly means that this is not the compound. Our actual compound is actually this one. And if you actually check the compound, there's 3 carbon atoms, right? Total.
Yeah.
And 3 of them have different chemical environments. All right.
All
And
right.
this chemical environment and this chemical environment, they're the closest to each other. They're very close because they're all joined with carbons and hydrogen, but there still is some
Yes.
difference, right? Which is why you're
Yeah.
getting these two values, which are sort of close but not really identical. There's still some differences between them. Is this fine, or is this making sense?
Yes. It makes sense.
Okay, okay. So a few more examples. We'll look at two more examples, and then I'll move on to the hydrogen NMR. Because if you don't understand this one properly, then hydrogen NMR is more difficult. So I don't want to, like, let's just do this properly, and then we'll move on to hydrogen NMR.
All right.
Let's see. Okay, I have a good example here. Okay, so let's see. Okay, so this is one of the graphs. Imagine you are given this graph and you are given this information. They've given you one molecular formula, right? That you
Yeah,
can decide from. So they've given you that, and they've given you this graph. Okay. So now what you have to do is you have to try to figure out. You have to try to figure out what is the possible structure. What possible
yeah,
structure, or what can the actual compound? What might the compound look like? All right. So
all right.
let's go through this. So first of all, we can see there's like 3 to 4 different peaks, right? 4 different peaks. One of them is very small, like the one that is at zero is very small, right? This one,
Yeah,
it's very small. Now this one we will ignore, okay? We're going to ignore the peak at zero. Do you can tell me why? Why shall we ignore the peak at zero? Because if you remember last class, we talked about a compound known as TMS or tetramethylsilane.
yeah,
Now tetramethylsilane is a reference compound. That is, whenever you're doing this experiment, you will intentionally give some TMS with your sample. So imagine you have some compound, compound X, compound Y, compound Z, whatever compound, you don't really know what it is, okay? Some unknown compound. You give that into your machine, obviously. Along with that, you're going to give small amount of TMS, okay? Now, it's a reference compound. What does the word reference mean? That means you are going to compare everything with this, all right?
yeah,
So the peak at zero, we can actually ignore. It's not important to us. Is that fine? Now, apart from that, you're getting other peaks. So let's just try to decide. So this peak can be like around 60, right? This can be like very close to 60, approximately close to 60. Yes or no?
yeah,
This peak is it's a bit less than 25, right? Because the midpoint is like around here, somewhere around here, right? This is like the halfway
yeah.
point between 0 and 50. So let's say 23, 24, maybe. It's okay. You can be like approximately. Let's say 23, no problem. And what about the other peak? What value do you want to give that? Like 10, maybe 10, 12.
Yes.
10 or 12 would be fine. So let's give 11, no problem. Let's give 11. Okay, so we have 3 different peaks and we have a good approximation of the values of the chemical
Yeah,
shift values 60, 23, 11. So now what you do is you have to come to this graph, this table which is given to you, and you have to compare the values. So 60, at 60 there's two
yeah,
possibilities, this one and these bonds, right? These are the two possibilities at 60. This is also slightly possible because if you draw a line at 60, right? If you draw a line at 60,
yeah.
then it's like very close, but it's not really exactly there. But uh, sure, no problem. Let's consider it. Now, out of these 3 possibilities, what do you think? We should ignore some of them, or which one can we consider? Which one can we ignore? What do you think? I mean, they've given you the molecular formula, right? C4H10O. C4H10O. So based on this molecular formula, what can you decide? Do we consider all 3 of these, or do we just ignore some of them? Consider some of them. What can we do?
Ignore some of them, consider some of them.
Yeah, which ones? Which ones? Which ones do we ignore?
Like the zero will be ignored.
No, 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 not that, not that. I'm telling you that we have 3 different values, right? 60, 23, and 11, right?
Yeah.
Now we're trying to use those values and trying to find out what bonds are available. So at 60, you can see there's 3 possibilities. This is one possibility, this is one possibility, and this is one possibility. Okay. Out,
Okay.
out of out of those 3, which ones can we ignore? That's what I'm asking you.
Oh, all right.
Yeah. I mean,
Uh,
you take help from the molecular formula. Use the
yeah,
molecular
yeah,
formula
yeah.
and then yeah.
I think that 11 part probably.
No, 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 no. Uh, we are only considering the value at 60 now. Forget 11 and 23.
Oh,
At
all right.
60, there are 3 different bonds. We have carbon nitrogen bond, carbon OH bond, carbon halogen bond. Which bond can we consider? Which bond must we
The
ignore?
carbon
That's what I'm
carbon,
asking.
the carbon carbon bond.
Yes, we are not considering that. I did not circle that. Out of the
Yeah,
ones
yeah.
that I have circled, out of the ones that we have circled, out of these 3, we have to ignore some of them. Which ones? That's what I'm asking you.
Oh, all right, all right. Um,
Again, use the molecular formula, that will help.
Uh, Probably the carbon chlorine bond and bromine bond.
Yeah, we can ignore the halogens because my molecular formula has no halogens, so that doesn't make sense at all.
Yes. Yes.
Also, this one can be ignored. That doesn't make sense as well
Yeah, yeah.
because no nitrogens. So I am confident that this structure has a COH bond, right? We are confident it has a COH bond. Okay. Um, and then we have two other peaks which are at 23 and 11, right? 23
Yeah.
and 11. Now 23, 11, 23 is like maybe like here, somewhere around there, and 11 is like here. And they're both correspond to this bond only, right? They both correspond to this bond only, which is carbon-carbon single bond. Yes? Are we clear on that? Like 11,
Yes.
23 is here, 23 is here, and 11 is approximately here, all the way here. So at those values of chemical shift, only carbon-carbon bond is there, carbon-carbon single bond is there. No other bonds are really there. So we know that there's carbon-carbon single bond.
Yeah.
So there's carbon-carbon single bond. So now let's try to draw the structures. Okay, let's try to draw the
All right.
structure. So carbon-carbon. So there's 4 carbon atoms. So let's draw it like this, and then OH. So we CH2, 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 CH3. Is this fine?
Yes.
So this is one of the possible structures. Okay, this is one
All
possible
right.
structure. Now, apart from this, there's another possible structure. The other possible structure is CH3, CH2, CH, and then OH joined here, and then CH3. What do you think? This is one. This is also possible, right? Because it
Yes.
also has OH bond and everything. So this is also possible. Very, very completely possible. And what else? What else is possible? Let's see. Uh, let's say this is joined to carbon. This is joined to a carbon again. Uh, let's see. This is joined to CH3, CH3H, CH2. This is also possible. Like they, all three of these molecules have the same molecular formula. They're matching with the molecular formula. This one, as well as this one. They all match with the molecular formula C4H10O. Can you see that?
Yeah.
Now the question is, which one will we choose? All right, which one is possible? Which one is correct? Now, from the graph, how many different chemical environments did we get, or how many different peaks? Ignoring the peak
We
at
got
0,
three
obviously.
three
Three.
different picks.
So there must be 3 different chemical environments, right? There has to be
Yes.
3 different chemical environments. Now, consider the green structure, okay? Consider the green structure. In the green structure, all right, forget that. Consider the red structure, okay? In the red structure, um, this carbon has a specific chemical environment. This one has another chemical environment. Yes or no? This one has another chemical environment, this carbon
Yeah.
atom, and finally this carbon atom. This
Yeah.
is
Yeah.
another chemical environment. So there are 4 different carbon atoms, and they all contain different chemical environment. Do we agree or not? Do we get that?
Yes.
So is this
Yeah. Yeah. Yeah.
possible? Is it possible that this structure gave you this peak, or is it not possible? Is it possible that this red colored compound, the compound that is I've highlighted in red, that gave you that
Yeah.
graph? Is it possible or is it not possible? What do you think?
I guess it's possible.
It's not possible because there's 4 different carbon environments, but we got only 3 different peaks. No,
Yeah.
we got 3
Yeah.
different peaks, but this compound has 4 different carbon atoms with 4 different environments. So if this was actually the compound, then we would have gotten one more peak extra, but we didn't get that. Is that fine?
Yes.
Okay, so that means this one is not correct. Look at the blue colored compound, all right? Blue colored. Focus on the blue colored one now. This carbon has a specific chemical environment. This carbon has a specific chemical environment. So does this one, and so does that one. Yes.
Yeah.
So you have the carbon atoms, and each of them are still having different chemical environments. So this one is also not possible because we must get 4 different peaks if this was the compound. What about the green colored one? Can you please discuss? I want you to discuss it. Consider the carbon atoms and discuss how many different chemical environments there are. What do you think?
Uh,
Hello?
Sorry, sir. I was having internet issues. Do you mind if you repeat?
Yeah. So the green colored compound, that's the left. So can you discuss based on what carbon atoms there are, how many different chemical environment there are?
Um, like, can you repeat based on the green color? Like, sorry,
Yeah, yeah,
there's a
yeah.
lot of lagging going on.
Yeah. Consider the green colored compound, all right? And
Yeah.
what you have to do is you have to check how many different chemical env- environments there are. So like total, I can see there's 4 different carbon atoms, right?
I guess there are three different.
Yes, one.
Yeah.
Keep saying.
Like, I guess there are three different chemical environments in the green colored one.
Okay. Okay. Tell me which carbon atoms are same. So I've numbered them for you. You can tell me which carbon atoms have the same
H
chemical environment.
1 and 3.
Give me the number. 1 and 3. Yes. So this carbon atom and this carbon atom have the same chemical environment. They are
Yeah.
responsible for one peak. This is responsible for another peak. This is responsible for the third peak. So that means this is a possible structure. This is the structure that makes the most sense with the graph. Is that fine or not?
Yeah. Yes.
Did we understand this whole thing?
Yeah. Yeah.
All right, all right. So that's it for carbon NMR spectroscopy. I have a lot of examples actually, but we'll just move on to carbon, sorry, the hydrogen NMR. I might give you this PDF, which is, there's a PDF. So this is officially from Pearson. It's a good PDF if you want, base like more details. And there are other additional examples also. So I'll give the link to that. You can go through
All
that.
right.
So now we'll just move on to proton NMR. So far the NMR that we have been doing, this NMR, we are considering only the carbon atoms. All right, we are only considering
All
the
right.
carbon atoms. Now that is known as carbon 13 NMR.
All right.
Now what we will be doing is we'll discuss what is proton NMR. Proton. Why is this red? Proton NMR. Now it's called proton NMR because we consider the hydrogen atom, all right? And hydrogen atom, apart from the nucleus, it's just a nucleus with a, without the electron, a hydrogen is just a nucleus with a one proton. So it's also known as called as a proton. So we talked about this last class that NMR, when you do NMR, the atoms that you target, they must have odd number of nucleons, all right? Odd
All right.
number of nucleons. What is nucleons? Nucleons has neutron plus proton, okay? And hydrogen only has one
Okay.
proton, right? One proton and zero neutron.
Yeah.
So overall one, right?
Yes.
So that this is odd, right? This is odd.
Yes.
So hydrogen is, it's possible to target hydrogen when you're doing NMR spectroscopy. Okay, that's what we'll be doing.
All right.
That's what we'll be discussing now. Now, proton NMR are of two types. There is one of these like low resolution proton NMR, which is actually easier. This is the easier one. And then we
Mm.
have high resolution NMR. High resolution, maybe we'll discuss tomorrow. I'm not sure. Depends on how long it takes to explain that. High resolution NMR. Now, today we'll start with low resolution NMR today. Now, and then if we get time, we'll
All right.
talk about high resolution as well. Also, what about did you go through those the homework questions, those practice questions?
No, sir. Basically, I couldn't go because today I had two classes
Yeah, yeah. Okay,
and
sure.
the 1.21, the CH3 one.
Yeah. So the reason that that is the largest is because if you consider the number of hydrogen that is actually responsible for that peak, it's actually six, because there's three here and three there. Total, how many hydrogens are actually responsible for that peak? Six total.
Six.
Six. And the other two peaks, they're only due to the one hydrogen each, right? One and one.
Yeah.
Do we understand so far that the larger the peak, the greater the number of hydrogen that is responsible for that peak? Is that fine?
Yeah. Yeah. Yeah.
Okay. Some more examples. Let's do butanol. So butanol is something like this, something like that.
Yeah.
So here again, if you check, there's I want you to tell me how many different chemical environments and how many different peaks do we expect?
Sorry, sir. I didn't hear you properly here.
Yes, so from the structure that is like butanol, how many different
Yeah.
chemical environments, and as a result, how many different chemical like peaks do you expect in the graph for butanol?
Uh, uh, four or three or four probably.
Three or four? Okay, one.
Yep. Most probably
Will be
four.
more, yeah, it will be four actually. It will be four. It will be four. Okay, so
All
let's go
right.
to this. So CH3, CH3. This is this one. Okay, and then
Oh,
this one is CH2, this one is CH2 as well, but still, even though they look similar, the chemical environment is different. Why? Because if you consider these two hydrogen, right, on the left side they're joined with CH3, on the right side they're joined with CH2. Okay, but if you consider these two hydrogen atom, okay, on
yeah.
the left side they have CH2, but on the left side they have
All right.
CHO. So so what I'm trying to explain here is, although they themselves are same, both of them are CH2 CH2, the hydrogens are kind of similar, but it's not about them, it's about what's around them. All right, so you can see that
All
one of the
right.
CH2 on the left side there is CH3, other side there is CH2, but for the blue color one on the left side right side is different, right? The surrounding is different,
Yes.
which is why we will consider them as different chemical environment. So as you can see here in the graph, you're getting actually two different peaks for CH2. Both of them are actually responsible for CH2. All right. And finally, you have the
All right.
aldehyde functional group. This hydrogen, this is for this peak. All right.
Yeah.
And you can see
All
which one has
right.
the highest like area among the peaks. Which one is like the greatest area? The CH3 one, right?
Yes.
Because which hydrogens which are actually responsible for that single peak? whereas the other ones it's like two hydrogens or one hydrogen. So since it has the most number of hydrogen responsible for that peak, the area under the peak is greater. Is that fine?
Yes.
All right, all right. Um, so low resolution NMR is this much only. I don't really think there's more to show. We can move on to high resolution NMR. Um, high resolution NMR is like that, a bit confusing, but I'll take it a bit slowly, take it step by step. Um, so first question, or like the first question that you have is, what's the difference between high resolution and low resolution NMR? So we'll now look at high resolution proton NMR. So remember, we're still considering the protons, right? We're still considering hydrogen atoms. The only difference
Yeah.
is it's higher resolution. Now, what's the difference between a low resolution NMR and a high resolution NMR? The main difference is in the graphs. The main difference is in the graphs. So like the chemical environment, how many peaks, number of peaks, those are still same. But the difference is actually in the peaks. Something happens. So in low resolution NMR, only peaks are visible, all right? Only peaks are visible.
All right.
But with high resolution NMR, what will happen? The interesting thing that happens here is you're going to get peaks, but with the peaks, you're going to get splitting pattern. Okay, you're going to get
All right.
splitting
Yeah.
pattern. Now, what does this mean? So your peaks can be split. So what I mean by that is, imagine you have a single peak. Okay, single peak. This is what
All
the
right.
peak looks like, for example, in a low resolution NMR. In high resolution NMR, the peaks will be like this. They'll be like this. They can be like this. Sometimes the peaks are also like this, like two single lines or one single line. So the peaks are more detailed. All right, there's more information that can be obtained from
All
the
right.
high resolution peaks, because the most important thing is they're split. The peaks get split. So what we have to know specifically from high resolution NMR is what the splitting patterns actually mean, or when you look at a graph, what does the splitting pattern actually mean? So let me show some examples. 1 minute.
Because CH3 one is attached to a carbon and the other is attached to CH2.
Yeah, so the one of them is going to CO bond, CO group. So even though
Yeah.
they themselves are same, the environment, the surrounding is not same. Okay, so that means if you expect a peak, like if you expect the NMR spectroscopy, right? How many different peaks do you expect from this diagram for this compound?
Yeah.
How many peaks? How many peaks
You
do
mean
you
like how many
expect?
different peaks?
Yes, yes, yes. How many
Uh,
different peaks can we expect?
I guess two.
Mm, yes, two peaks. So one peak will be responsible for the 336 hydrogen atoms. So that can be like a fairly large
Yeah.
peak. Another one is just the CH2, which will be a somewhat a smaller peak, right? Now,
Yes.
now, here's the interesting thing. The peaks that you see here, this is actually what the peak will look like for a low resolution NMR. Okay, but
All right.
for a high resolution NMR, the peaks will not appear this way. The peaks will not appear this way. So what will happen? Instead, you're going to get peaks that look like this. You're going to get peaks that look somewhat like this. So for the CH3, right?
Yes.
Oh, 1 minute, 1 minute. I made a mistake. Did I just say two peaks? There will be three different peaks. My bad. One peak for them, one peak for them, and one peak for them. There will be three different peaks. Why did I say two peaks? I'm very sorry about that. There will be
All
one,
right.
two, three different peaks. Okay, three different peaks
All
for
right.
three different chemical environments: A, B, and C. Is that fine?
Yes.
Okay. But see, here's the thing: this type of peaks you only get with low resolution NMR. For high resolution NMR, the peaks will be slightly different and more informative. How? Let's consider A, all right? Position A.
All
Position
right.
A is like these ones. So how many hydrogens there are? How many hydrogens?
It has 5 hydrogens.
Um, five, no, three. CH3, that's a
Oh, you
CH3,
mean the
right?
cir?
Yeah, the circle part. Just the circle part.
Yeah, yeah,
CH3. So there's three hydrogen atoms. Okay. Now, what I want you to tell me, so what I want you to tell me is those three hydrogens are joined to a carbon atom, right?
yeah.
Now, what is the neighboring carbon atom to that carbon atom? So the carbon atom that those hydrogen atoms are joined to is this one, right?
Yeah.
Who is the carbon atom that is next to this one? Which carbon atom? That is next to this. This one, right? This blue colored carbon atom. This carbon atom is the atom. It's the, we call this the next door carbon atom, okay? Next door.
All right.
Call this the next door carbon atom. Is this fine or not?
Yeah, yeah.
Okay. Now tell me, this next door carbon atom, how many hydrogen does it have? How many hydrogen does it have?
The next one, like you mean like the carbon?
The blue, yeah, the blue one. The blue one is the next door hydrogen carbon atom, right?
It's bonded to the one carbon only.
Yes. So this carbon, does it have any hydrogen or does it not have any hydrogen?
Yeah, it has 2 hydrogens.
No. I'm talking about this one. This one.
Yeah.
Does it have any hydrogen or not?
No, no. This carbon has no hydrogen.
Okay. Why did I choose this carbon to talk about? Because it's the next door carbon atom to this one, all right?
Yeah.
To this one. So this next door carbon atom has no hydrogen. So what you do is you have to follow this formula n+1, okay?
All right.
And you just told me that the next door carbon atom has no hydrogen, right? Zero hydrogen.
Yes.
So you'll do 0+1. How much do you get? How much do you get? We get 1. 1, yes?
Yeah.
And so for those three hydrogens that are inside the circle, you're going to get a single line, all right?
All right.
A single line. Is that fine?
Yes.
And we call this a singlet. We call this a singlet. Okay. Now consider the other hydrogen. Let's consider these, okay? The one that are inside the red color circle. There, how many
All right.
hydrogens there are? How many hydrogens there are?
The red color circle has 2 hydrogen.
Two hydrogen, and they themselves have a specific chemical environment that is unique. Yes,
Yes.
the chemical environment. Yeah. Now, those two hydrogen atoms, they're joined to a carbon atom. Yes or no?
Yes.
Which is this one, the one that I'm modeling right now. This one.
Yeah.
Okay. Now, I want you to tell me who is the next door carbon atom to that one. Next door to that one. Next door to this one is this carbon atom, like the neighbor. Who is the neighbor of this carbon? This carbon and this carbon, right? These are the two neighbors.
Yes.
Are we clear or are we not clear?
No, no, I'm getting it.
Okay, now I want you to do is 2n plus 1, where n is the number of hydrogen on the neighboring carbon atoms. So the neighboring carbon atoms, how many hydrogen do they have?
The neighboring carbon atom, it has three hydrogens.
Three. The one on the left doesn't really have anything. The one on the right has three hydrogens. So we'll do 3 plus 1. Is that fine?
Yes.
So how much do we get?
Alright.
4. We get 4.
Yes.
4, yes. Okay, so for
Four hyd
since it's okay, so since it's 4, remember we are still considering these hydrogens only, right? The hydrogens that are inside the circle,
Yeah.
inside the red circle. And for them, the peak that you get, it will have 4 splits, all right? It will have 4 splits. So it will look something like this. That, that, like that. It will be something like this. 4, oh, 4 splits, okay?
Yeah.
Why 4 splits? Because the value of n was 4. As simple as that. All right. I will not go into more details and make this any more confusing because we don't need to know the details. And this is known as a quartet. Okay.
Yeah.
Quartet. Why quartet? Because there's 4 splitting patterns inside the peak. You can see. Is that fine or not?
Yes.
All right. Finally, we have the other hydrogen atoms, which are these ones, right? These hydrogen atoms. They will
Yeah.
also give you a one peak. Okay. Now, to understand their peak or their splitting patterns, you have to look at their neighbor. Who is their neighboring carbon? This one, right?
Yes.
And how many carbon, how many hydrogens is there on this neighbor?
The neighbor has two carbon atoms.
Two
You
carbon.
mean the
Excellent.
CH3 has?
No, not the, yeah, yeah. We are considering the hydrogen inside the CH3, but we are going to consider the
Yeah.
neighbors this time. Always neighbor, neighbor.
Yeah.
Look at the
Yeah.
neighbor. Neighbor has 2. So if you do n plus 1,
Yes.
that is 2 plus 1, and that's 3, right? That's 3.
Yes.
So the peaks will be like this. And this is called a triplet. Okay, triplet.
All right.
Why triplet? Because you can see that this peak is split into 3 different sub peaks. All right, so
All
the,
right.
like, rather than being a single peak, it is broken down into 3 smaller peaks. Is that fine or not?
Yes.
Okay, now overall you can still see how many overall peaks do we have. Overall 3, right? Like,
Yes.
ignoring the splitting, ignore the splitting, there's 3, which is similar to the low resolution as well. In low resolution we got 3 also, right?
Yeah.
But what is the advantage with high resolution NMR? You are getting information about their neighbors. Is that fine or not?
Yes.
All right. So this is what patterns, this is the type of patterns you can expect. I know it's a bit confusing. So apart from singlet, quartet, and triplet, you also have other patterns. So let me give you that example. So this is from your student book only. Um, this will be all the patterns that you need to know. All right.
All right.
Singlet, doublet, triplet, quartet. I think there's more actually. I like, for in your textbook, this much is given only. But if n is 4, sorry, yeah, in if n is 4, then n plus 1 is 5, right?
Yeah.
And for n plus 1, 5, I think it's called, forgot what it's called. Wait, it's called, I myself forgot. 1 minute. I have it written. It's unfortunate. I don't really know why it's not in the textbook. When I studied this in my like, I have it in my copy. So it's called quintet. Quintet. So for 5, it's known as, again, don't have to worry about this. I will try to include this in the notes. And
All
so
right.
these ratios, right? I'm probably a bit confused about what this ratio of peaks means. So let me explain that first. So in the example that we saw, we have a quartet, right? We have a quartet, and in
Yeah.
quartet, these are the ratio of the peaks. 1 is to 3 is to 3 is to 1. That means this is 1, this is 3, this is 3, this is 1. That's the ratio of how long each line is. That's why. Okay.
All right.
Consider the triplet. In triplet, what does the ratio look like? 1 to 1, right?
Yes.
Because the lengths are 1 is to 2 is to 1. That's why. Okay.
All right.
So depending on what pattern you have, you can actually predict the type of the length of the peaks that you get. One more thing, when we actually looked at this example, these three hydrogens gave you this peak, right?
Yeah.
And can you see that the length of the line is comparatively higher than the one in the middle, because these two hydrogen give you this peak, right?
Yes.
And those three hydrogens give you this peak again. So you
Yes.
can see that the length of the peak, the length of the pattern is depending on how many hydrogen actually give you that. Okay,
All
this
right.
is fine or not?
Yeah. Yeah.
Okay. So for quintet, if I write this down, the ratio is 1 4 6 4 1. So it's 1 is to 4 is to 6 is to 4 is to 1. Don't you have to worry about memorizing this. Okay, it's just giving
All
this
right.
because this is known as sextet, and the ratio is, it's very complicated. It's 1 5 10 5 1. Again, don't even have to memorize the values. Okay, by the time we are done, you will you will be familiar with the shapes by then, so don't have to memorize these values. These are just given because I, you know,
Yeah.
um, yeah. So that's the pattern that usually we get. Now let's look at some examples. um, let's see. In, um, this is the NMR for ethanol. Okay, hydrogen proton NMR.
Yeah.
So let's draw the structure of ethanol and we'll explain. So let's say ethanol is C2H5. So there's CH3, two. Okay. This is the what you can expect. So this is the structure of ethanol. So these three hydrogen atoms all have the same environment, right? They will be responsible
Yeah.
for a single peak. These two hydrogens will be responsible for one peak, and this one will be responsible for another peak. So three different chemical environments. We understand that, right?
Yes.
Okay. So let's try to find out the splitting pattern. Okay. So for the red colored ones, okay, look at the neighboring carbon
Uh,
atoms and tell me, for the red colored hydrogen atoms, tell me about the neighbors, their neighbor. So the red colored hydrogens, they're joined to this carbon, right?
yeah. The
Who is the
neighboring one
neighbor?
has
The neighbor is this carbon. The
yeah,
neighbor has how many hydrogen?
two
Two
hydrogens.
hydrogen. So the value of n plus 1 will be 3, right? 2 plus 1 will be 3. So this must be a
Yes.
triplet. It must be a triplet pattern. All right? That's 3.
Yeah.
And then look at the green color one. If you consider the green color one and then look at the neighbors. Look at the neighbors.
So The neighbor of the middle carbon has one hydrogen.
Uh, what about the other neighbor? It has two neighbors.
Oh yeah, the first one has three hydrogen and the other has one.
Uh, three hydrogen, one.
Like
Wait.
O is
Yeah, sure. One. Yeah, as you're saying. Yeah. Keep saying. The OH, please. Hello. Yeah. So the green for the green color ones. If I do n plus one, neighboring hydrogen atoms, how many?
uh there's one with O and the other one with the first
Yeah.
carbon.
But okay. Yes. Yeah. You are correct. And we will not consider the OH. All right. As the neighbor.
All right,
Only the carbon
all
neighbor.
right.
So three, right? So three plus one is four. So we can expect a quartet. Yes.
Yeah.
And finally, you have the purple one, the purple hydrogen. And for the purple hydrogen, the neighbor has two hydrogen, right? Neighbor has two hydrogen.
Yeah.
Neighbor has two hydrogen. So that's two plus one, that's three. So this will be triplet as well. So we can expect one quartet and two triplets. And you can see here, wait, I might have mistaken this. 1 minute. Uh, okay, one more thing, my mistake. So so for OH, okay, so please listen to this carefully. For OH, the hydrogen, it will give you a peak, okay, it will give you a peak, it will give you a peak, but there will be no splitting, okay, no splitting, just single peak, okay, no splitting. Is that fine? So the usual rules you can follow only for the hydrogens that are joined to carbon atoms. Is that fine?
Yes.
All right, so we can expect a triplet, a quartet, and a single line. So let's follow, let's look. So you can see here the two hydrogen atoms. Does this look like a quartet to you? Does this look like quartet to you? Like there's probably one, two, three, four. Four splitting patterns, right? If you look closely.
Yeah.
Like, does it look something like this? Something like this? Does it look like that? Within this small region? Does it kind of look like that? What do you think?
Yeah.
And you can see the quartet. Do you understand the quartet? Why I'm calling this quartet? Because there's one, two, three, four. Total
There are
four
four.
splitting
Yeah.
patterns together. Okay.
Yes.
And they are responsible. Who is responsible for this pattern? The two hydrogen atoms. All right. These
All
two
right.
hydrogen atoms. This one and this one. Right. Remember the green color ones? There are two
Yes.
hydrogens themselves. All right. And then one OH. One OH is from this one, right? One hydrogen is from this OH part. This hydrogen
Yes.
alone. So you see, its pattern is not splitting. It's only one single line. If I look a little bit closer, it's just like one single line, right?
Yes.
So and finally, you will get another triplet. We'll get triplet from where? From these three hydrogen atoms, right? We'll get triplet.
Yeah.
And if you look at their pattern, which is like for the three hydrogens, it's actually triplet because you can see there's like overall, like I'll zoom out, you can zoom in with your hands. You see there's like one, and then two, and then three lines. So like it somewhat looks like this. if you look from very far away. Can you notice this? Like, is it visible?
Yeah.
So we call this a triplet. Now, although there are small like distortions inside, right? So these are small distortions. We will not consider them. All right. It's not possible for us to
All right.
differentiate these with our own eyes. All right. So you can just look at the overall structure.
All right.
Also in your exam, also in your exam, the diagrams won't be this difficult. They will be like more easy to understand. So don't worry about that. Okay. Like the diagrams, the lines will be more easily distinguishable. So it won't be a problem. Um, let's look at some examples. Um, let's take one example from your student book. Okay, so this is an easier example, easier to understand. So, okay, to solve this, you're going to need the table, I guess. Let me give you that table. Um, just a minute. Yeah, so you can see the graph here, right? The NMR spectrum. Again, this actually high resolution, okay? Why high
All
resolution?
right.
Because you can see that the individual peaks, they're splitting, right?
Yeah.
Do you notice? So this, again, this is an example of a high resolution pattern. So we're going to have to use this pattern to sort of try to predict the compound. So they've given us the molecular formula, which is C4H8O, 4H8O2 actually, C4H8O2. And so let's try to discuss. So from the graph, what information do you get? From the graph, you get the information that there are three different chemical environments. Yes or no?
Yeah.
Why? Why are there? Why do I say that there's three different chemical environments? Because there's three different regions, right?
Um.
Although the fat peaks themselves are splitting, um, there are overall three different regions. Yes or no?
Yeah.
Okay. Now let's look at the individual values. So we have one peak at around 4.1, 4.2, something like that, maybe, right? This one. This one is at like 4.1, 4.2, somewhere around that value. Do we agree or not?
Yeah.
And then we have another one here, which is at like 2.1. Yeah. And we have another one here, which is at around 1.4, 1.5. Do we agree so far?
Yes, sir.
Okay. So now based on these values, you're going to take help from the table to identify the bonds. So 4.2. So 4.2 is like here. So 4.2. What bonds are matching for 4.2? What do you see? It can either be like 4.1, 4.2.
Yeah, I guess it can be 4.1 or 4.2.
So it's like best matching like this one or this one, right? These two.
Yeah.
Now I can ignore this one because this is halogen. So we need to consider this actually because we don't have halogens, right? Now
Yes.
this here, what functional groups are they talking about here? Alcohol, ether, or ester, right? Now don't worry about what an ether is. We haven't discussed ether yet, but we have an idea about what alcohol or ester are, right? That means this
Yeah.
hydrogen, the hydrogen that that we are dealing with here, and this hydrogen must be responsible for the OH group.
Yes.
OH group. So and and consider this splitting pattern. What type of pattern is this? Singlet, duplet, triplet, quartet? What can you notice from this one? Just focus on this one for now. What do you see? See quartet. If you can you tell me if you agree? I can see a quartet because there's four individual smaller lines, something like this. Yes or no?
Yeah.
So we agree that this is a quartet. So how many neighboring hydrogen atoms are there? How many neighboring hydrogen atoms are there? If it's quartet, that means
There
n
are.
1 was equal to 4. That means n was must have been 3. Yes.
Yeah.
So that means there was probably a carbon. There was probably a carbon that had hydrogen, and next to this carbon there was another carbon to which my hydrogen was joined. And to be specific, how many hydrogen? Two hydrogens.
Yes.
So something like this. Let's see. CH2. That means what I'm trying to say here, that there were two hydrogens who are responsible for this peak. Why is this peak a quartet? Because neighboring carbon atom had three hydrogen atoms. Is that fine?
Yeah.
Okay. Um, and then consider 2.1. 2.1, I think most possible is alcohol, right?
Yeah.
Alcohol. This is O4, O2. I did write O4. Alcohol. So, and what about the splitting pattern of this line? Do you see any splitting pattern or do you see no splitting pattern? Is it just one single line?
Uh, it's just one single line.
One single line. That means this must have been OH. This must be an hydrogen joined with O. Yes or no? Or um, or something like this. Look at this. What did they say here? Three, right? Three. Do you see the three written on top of the peak? Can you see the three written on the peak?
Yeah.
That means three hydrogens were responsible for this peak. All right.
Yeah.
So three hydrogens joined to the same carbon were responsible. And since there is no splitting pattern, that means this carbon must have a neighboring OH group, perhaps. Yes or no? Maybe it was joined to COH group, or it could also mean that it's joined with carbon that is joined with oxygen because this doesn't have any hydrogen. That means the neighboring carbon doesn't have any hydrogen. That's what's the situation. Do we understand slightly? I know it's a bit confusing today's class. We'll probably have to go through the video.
Yeah.
My understanding. But why am I drawing this? It's because there's three hydrogen atoms and the neighboring carbon has no hydrogen. That is what I would like. Why would I like that? Because the
Alright.
line is one line. So n plus one is 1. That means n must be 0, right?
Yeah.
Neighboring hydrogen atom should be 0. That's why.
Yeah.
And finally, 1.4. At 1.4, you only have this one alkane. So it's like, how many hydrogens responsible? 3 hydrogens. That means
Yes.
CH3, they must. And what about the splitting pattern? What does this splitting pattern look like? This splitting pattern. Singlet, duplet, triplet, quadruplet. Like how many
Triplet.
individual triplet? Yes, that means neighboring carbon atom must have two hydrogen atoms, right? Because n plus 1 was 3, so n must be 2. What do you think? Now, if I take these individual groups and if I try to join them together, try to make a compound out of them, let's see what's the most possible explanation. Something like that, right?
Yeah.
And you have that. So I cannot really stick them like this, so I probably have to reinvert this. So something like that, like CH2 will be on this side, CH2 on that side. And how many oxygens were there in the compound that they told us? 2 oxygens, right? That means it could be an ester because we know ester has functional group COO, yes? Like this. So maybe this is joined to another oxygen and so on. This could be a structure. Do we understand so far?
Yeah. Yeah.
Now, there's a few problems here. That is, total carbon number should be 4. So we have to exclude some part. So this must not exist. This must be joined with them. 1, 2, 3. 1, 2, 3. Let's see. 1, 2, 3. 4, CH2, CH3. I guess we can control that as well. 1, 2, 3. So, okay. How many overall peaks there are in the graph? 1, 2, 3. Yes.
Yeah.
So how many different chemical environment? 1, 2, 3. Is that fine?
Yeah.
This hydrogens, there are 3 hydrogens, but their neighbor has 2, so this must be triplet. There's 2 hydrogens, but their neighbor has 3, so there must be quartet. N plus 1 must be 4.
Yes.
There's 3 hydrogens here, but their neighbor has nothing, so they must be singlet because n plus 1 must be 1. So this must be singlet. Is that fine?
Yes.
Singlet, quartet, triplet. You can see in the graph. If you take a very close look, you can also get singlet, quartet, triplet. So you can see here. This is your singlet, this is your triplet, this is your quartet. Is that fine?
Uh,
So I think we understand what I mean by the patterns, but I think the part where we still didn't understand is how am I using the graph to figure out the structure, right? That
yeah.
part is still not understood. Yeah. So we'll just continue with that tomorrow. Okay.